Well, ladies and gentlemen, today it is our great pleasure to have Greg Adkins here with us. Greg got his degree from Santa Monica, from Los Angeles, at a time when Santa Monica probably was one of the most desirable places to live on planet Earth. He studied in the vicinity of one of the greatest of quantum electrodynamics, Julian Schreiner. His thesis advisor was Nina Byers, but he heard the wonderful lectures by the master himself. He then spent postdoctoral appointments at institutions whose name is as much resounding in our deep physical subconsciousness as UCLA, namely Princeton. There he worked with someone who's equally well known, Ed Witten, on Skirma models for nuclei, and wrote a few highly cited papers. He then went on to what I visited him there, one of the nicest places in Pennsylvania, and Franklin and Marshall College, named after Benjamin Franklin, a master diplomat and a master scientist at the same time. Today, it is our great pleasure to have Greg here give a talk on new methods to evaluate some of the most complex constructions in physics that mankind has come up with up to this point, namely Feynman integrals, and the application of these methods to the calculation of bound state energy levels of a very interesting system, Muonium, and of course, positron. Greg, it is our pleasure to have you here.
Oh. Yes, well, thank you so much. I have to say it's been a great pleasure to be here. I visited campus a couple times before, and this time it's special because I got to meet many of you and see some laboratories, hear some stories about really exceptional work that's being done here. And so I've been very impressed with the department and just kind of the atmosphere. So thank you. So yes, I'm going to talk about muonium, and I'll talk about what that is and why it's interesting, and some of the techniques that are being used to study it to higher and higher precision. So the idea sort of is to, well, ever since I would say maybe the discovery of the Higgs boson, which kind of filled out standard model predictions, since then there have been no, I think, outstanding discoveries at the largest particle accelerator, highest energy frontier. And so everybody is searching for new physics, for beyond standard model physics, and what hints can we find from various, in different ways that might lead to something that we don't know already. And maybe you could learn something about that by going to higher and higher energies, but that's very expensive. And there's no guarantee that you will find something interesting. So a less expensive way possibly to explore is something called the precision frontier, is to calculate and do experiments on some systems to higher and higher precision and see if what you think is the correct theory actually agrees, or whether you have to maybe find some new theoretical constructs or ideas or particles or forces or dimensions or whatever to explain experimental observations. So this is kind of in that line to look at muonium. Muonium is a bound system. It's a little atom, little exotic atom made of a positive muon and a negative electron, so it's an atom like hydrogen. So first I'm going to say just a little bit about the muon and then talk about this atom muonium. But kind of the point is that it's a relatively simple quantum system, so that there's a chance of being able to calculate to high precision. And it's a system which can be made in the laboratory and, studied. It's basically spectroscopy. You find what wavelengths are necessary to cause a transition from one energy level to another and relate that to the energy difference and so on. And so that's kind of the idea here, is to compare calculations, which I'm involved in doing, with experimental measurements. So first the muon, typically produced by pion decay. Many other ways of producing it, but that would be a typical way. It lives a very short time, 2.2 microseconds is its lifetime, at which point it predominantly decays to an electron or positron, depending on its charge, and some neutrinos. So that's the muon. There have been hints for many years that maybe there's something about the muon that's not quite understood. Specifically, the magnetic dipole moment, which has been calculated to high precision and measured. And in fact, there's a recent measurement to much better precision than before. And there's been a long-standing difference between calculation and measurement. Just a word about what was being looked at. The spin of the muon, which is spin 1/2, so there's a little spin vector in a quantum mechanical sense. And this is the magnetic moment. It's like a little magnetic dipole. It has a north pole and a south pole. And a strength, which is given by Q is its charge, mass is M is its mass. These are units where things like h bar and speed of light and so on are set to 1, just because you always carry them around and you can always reinsert them at the end when you need them. Anyway, so this is the Bohr magneton, and then G is a numerical factor, which would be 2 if the Dirac equation was exact in describing the muon. But it's not quite 2 because there are quantum field theory like corrections with virtual particles and so on. And this was the famous Schwinger calculation in the early days of quantum electrodynamics, which showed the initial correction of that anomaly. That's what A is called, the anomaly, the difference between G and 2. And that's the first. Okay, alpha is the fine structure constant, which is a measure of the electron charge, and which is a very small number, like 1/137 roughly. So if we make a perturbation series in alpha, we can then calculate this anomalous magnetic moment factor to higher and higher precision. And this is just the first term, which comes from what's called a one-loop diagram, where there's one virtual particle. There are terms which have 2 virtual particles, 3, 4, and 5 even. So those have all been calculated, and that's how this very precise number is found. The latest experiment from just a few years ago at Fermilab gives, if you look at how many significant figures there are, that the first many of them agree, but there's actually, between theoretical prediction and experiment, there's actually a difference, which is significant. 5 standard deviations. So that's like the usual idea of 5 standard deviations. That's now a discovery, that's something. But there's question about whether the theoretical, something about hadronic contributions to the calculation, whether those are done quite correctly. So it's not clear. this is not something to give out a Nobel Prize for yet. But it's definitely a sign that possibly the muon is doing something interesting. And, it's definitely something people say when they want to justify their work on a particular, problem. Anyway, so muonium now is, like I say, a little atom, a little exotic atom. It is like hydrogen, that is, there is one positively charged spin 1/2 particle, one negatively charged spin 1/2 particle. The muon is much more massive than the electron, about 200 times. So it's like hydrogen and hydrogen. The proton is much more massive, but it's not infinitely massive. So it's like hydrogen. What's better than hydrogen is that the proton has itself some internal structure. It has inside quarks and gluons, and it has a non-zero charge radius. And there's some questions about exactly what that size of the proton is. And so the proton has structure, and that complicates the calculations. Muons and electrons, as far as we know, are point particles. They have no size. It's hard to imagine that on a fundamental level is that, they'll always be point-like particles, but as far as anybody has ever seen, there's no internal structure. So that makes the whole thing simpler. On the other hand, the muon doesn't live forever. So you have to get right to it when you're doing your experiments. They don't just, like hydrogen would sit there in your trap for a long time. Muonium, you have to do your experiment quickly. But 2.2 microseconds is really not that short when you think about like fundamental limits like the Heisenberg uncertainty relation, relating lifetime and how well you can measure like frequencies or energies. We can certainly, this does not limit our ability to measure energies at the level at which people are now trying to do. So anyway, high precision measurements are possible, and I'm going to talk about calculation of those energy intervals. So if you know something about hydrogen, you know that there's the Bohr energy levels, the 1/n² minus 13.6 electron volts over n squared would tell you where n is a principal quantum number, which can be 1 or 2 or 3 and so on, would tell you what the energy levels are. So that's similar with muonium. We have n equals 1 levels, but because the electron and the muon have spin, the spins combine into either a total spin 0 when you take 1/2 and 1/2 and add them quantum mechanically. You can either get the difference, which is 0, or the sum, which is 1. So there are 2 spin states, and that's the ground state, the n equals 1, and then the 2 spin states. With n equals 2, depending on what the orbital angular momentum is and what the spins are, you can get a number of levels. And so this is a picture of what these first couple of, n equals 1 and n equals 2 levels are. Of course, n equals 3, 4, 5 also exist, but they have not been explored experimentally, as yet very much. Here's the most precisely measured, I think, interval, the ground state hyperfine splitting it's called. The size of that interval is greatly magnified compared to like the overall diagram. Anyway, a number of years ago, way back in 1982, 1999, there was some previous pretty high precision measurements of that hyperfine interval. More recently, so this is an ongoing experiment in Japan at J-Park, the facility there. You can see that the precision is not so great, but it's really a proof of principle kind of measurement. And there's two kinds of measurements. They're called low field and high magnetic field and low magnetic field. And this is a low field, which is a less precise light measurement. So anyway, this is just a number to show you that they can make the system and they can make measurements of it. But their goal is to measure this with an uncertainty of 5 hertz. Okay, so 5 hertz, this is in kilohertz. So instead of this 53, they're trying to push that down by a factor of 10, which is a significant improvement. And so that's actually my goal as a theorist, to be able to calculate expected values for this hyperline splitting to the same precision. So that sets the goal. That's their goal. However long it'll take them to reach it, but calculations don't happen instantly either. So, so anyway, that's their experimental goal. The current theoretical prediction has a relatively large uncertainty. But what's interesting about that uncertainty is that most of it comes about because the mass of the muon is not known perfectly well. So most of that uncertainty is due to the mass of the muon. The part of that uncertainty that's due to, maybe I'll go there. The part that's due to theoretical, actual calculational uncertainty is 85 hertz. And so that's what has to be compared with this goal of 5 hertz, the experimental goal. The rest of, at the end of the day, if by doing calculations, we're able to reduce that 85 hertz significantly, and then compare experimental theory, the idea is, because the theory is so sensitive to the muon mass, we should be able to get a much better value for the muon mass that currently exists. So this experiment should be able to be used to get a better value, like for the the books that show particle properties. Maybe they'll be able to reduce the uncertainty in the muon mass by a fairly significant amount. So that's kind of cool. So at least that can happen by this comparison. Otherwise, if we find that there's a real discrepancy that can't be explained by the muon mass, maybe that's something else. But anyway, I'm currently involved in calculations at this level of precision, where this is called the Fermi splitting. It measures energy differences caused by these kind of magnetic hyperfine type effects. And then alpha cubed is a small, remember alpha is 1 over 137. It's therefore a very small correction to that. And that number is 8.4 hertz if the coefficient is 1. So I want to find that coefficient, basically. I want to find what the coefficient of that term is. Sometimes I'm going to use the word recoil corrections, because this term is proportional to the ratio of the mass of the electron to the muon, which itself is a fairly small ratio. But this has to do with the fact that the muon is not infinitely massive, so it's not stuck at one fixed point. It's allowed to then move, and so this is sometimes termed a recoil correction that involves this ratio. Yeah, so anyway, that's the goal, is to be able to calculate all those kind of terms. So just very quickly, some other intervals that have been measured. This is sometimes called the growth structure. It's the n=2 to n=1 difference. That's been measured, and actually there's a current experiment called the NUMAS experiment at the PSI, Scherer Institute in Switzerland, which is aiming to greatly improve by a factor of 1,000 the current best experimental measurement of this interval. So that is also relevant towards for my work. And they're also measuring what's called the n=2 Lamb shift and expect to be able to get a better result than previous. So I won't go into all the details of that. I'd like to get to actually what people do to calculate these things. And we start off relatively simply with the Schrödinger equation. So this is the basic equation of quantum mechanics, you might say, that will allow us to, if we can solve the equation for the wave function psi and the energy E, we can then know what those energies are. And when we do that solve, we get down here what we might call the four energy levels. One factor that goes into this is something called the reduced mass, which is not just the heavy particle or the light particle mass or the heavy particle mass. It's the when you combine the two and allow both to move and you take that into account, you get this. It's an average in some sense, but it's almost equal to the electron mass. And so we have this reduced mass, and that lets the energy levels be minus 13.54 eV, as opposed to what would be the case for hydrogen, which is more like 13.59 or 13.6, which is a number that most people should know. 13.6. Okay, so those are that's the most basic calculation of the energy levels. So they start off at order alpha squared, these basic energy levels. Now we have to do corrections to that. One correction, there are corrections from a number of different places. One correction is from relativity, from special relativity, which would say that the kinetic energy is not just mass times 1/2 mass times velocity squared. It's not just that. It has there are corrections to that. Okay, so special relativity is one type of correction. And we're going to have to know something about typical speeds of particles in the Muonium state to be able to know how big that correction might be. So to calculate a typical speed, you might define a typical speed as the square root of p is the momentum divided by the mass. You might define that as a typical speed, so you must calculate the expectation value of this ratio p squared over the reduced mass, which can be done in different ways. P is, can be thought of as a by the de Broglie relation involving derivatives, or you can use the Schrödinger equation, p squared there, and solve for p squared over mr squared from the Schrödinger equation, and then calculate the expectation value of the potential. There's different ways of doing it, or variables here. Anyway, we find that the typical speed is like the speed of light times alpha, so it's actually kind of small. Okay, and depending on what the principal quantum number is, it can be smaller. Well, I say small. It's small compared to the speed of light. It's actually a large number of meters per second, but it's small compared to the speed of light. And so that's what we, kind of sets the scale for these relativistic corrections, which look like this. Kinetic energy is the relativistic energy minus the rest energy. And that can be written in terms of a small parameter, p squared over s squared c squared. And we can do a Taylor expansion of that, and we get p squared over 2m, which is the non-relativistic kinetic energy. And we get a correction. And there are more corrections, but we'll stop here for the moment. We get a correction, p to the 4th over 8m cubed minus. So to find how much that shifts the energy, we need to calculate its expectation value in the quantum mechanical state. And when we do that, we get a term which, because p is proportional to alpha, this is now an alpha to the 4th correction, which is small compared to the alpha squareds of the original 4 energy levels. So this is our first kind of correction. And there are details about it. It depends on the principal quantum number, the orbital angular momentum, and so on. Those are the details. It's alpha to the 4th correction. Relativity is not the only correction. There's also magnetism, recoil, virtual particles that might be produced in a quantum field theory. So this is just one that I wanted to kind of show. It's kind of more or less easy to comprehend where it comes from. Okay, so what do we actually do to calculate at higher precision, to calculate further, get all of the alpha to the fourth directions, go on to alpha to the fifth directions, go on to alpha to the sixth directions, and then alpha to the seventh, which is the level of current interest. What do you have to do? You have to start with some quantum mechanical theory, quantum electrodynamics, and the version of quantum electrodynamics that we use is called an effective field theory, non-relativistic quantum electrodynamics, which is most useful for calculating properties of non-relativistic systems, which we consider this to be non-relativistic because the speed is small compared to the speed of light. As we'll see, there are some coefficients that enter into that non-relativistic theory that we have to know their value of. We have to talk about a generalization of the Schrodinger equation. Sometimes it goes by the name of beta saltpeter, but this is not a QED, it's this NR-QED theorem. And then build a perturbation theory based upon that. It turns out that that this beta saltpeter equation in a certain approximation is exactly the non-relativistic Schrodinger equation that we want to solve. So that's a great place to start a perturbative expansion, and that's what we're able to do. And then there's some details about how to calculate the terms that you have to calculate that I'll come back to. Okay, QED, quantum electrodynamics. It's a theory, a quantum field theory is described by giving this the so-called Lagrangian, which tells basically it's a very compact way of describing the theory. You can see QED has a very simple looking Lagrangian. There's a term describing the electron field, that's this psi guy, which has a certain mass and a certain charge. It has some dynamical effects. There's a capital F describes the photons in a relativistic way. And then this is capital A is the vector potential. It is a coupling between the electron and the photon. So from the Lagrangian, one can get what are called Feynman rules, that when you put them together into diagrams using certain rules, you can find out what you have to calculate to calculate these directions. And so these are the Feynman rules of quantum electrodynamics. There's the photon can propagate, the electron or the muon can propagate, and that photon or muon can give off, since it's a charged particle, it can give off a photon or absorb a photon. So very simple rules, relative. This gamma is, okay, that's a complication. It's a 4x4 matrix that enters into the pictures. So these are 4 component objects, the size. I mean, there are certain complications. And this is a completely relativistically invariant theory. It's completely consistent with special relativity. So that's its strength, because in particle accelerators and high energy processes, you definitely want to have a theory which is relativistically consistent and so on. It's not a strength for calculating properties of non-relativistic systems like these, like muonium or hydrogen or something, because it's like too powerful. You have to somehow ignore all of the details of super high energy stuff that QED takes into account and focus on the low energy physics. And QED itself does not do a good job at allowing you to do that. So instead, we use something called an effective field theory, which is named non-relativistic QED, which is where effects, well, basically, it is equivalent to QED for low energy processes. It's not to be used for processes that are high energy, like electron mass and above. It's not to be used for that. That's not its purpose. It's not actually, it's by definition pretty much cut off at energies like the electron mass and above. So it's not to be used for the high energies, but for low energies, you can see that there's actually an infinite number of terms here in Lagrangian. It's much more complicated than pure QED. So you might consider that a disadvantage, but the various contributions here are much more physical in a sense that for low energy processes, you can identify what you're looking at much more easily. And they are, even though there's more of them, the contributions that each one of these makes is easier to calculate than in full QED. The Feynman rules, this is just the first bunch of them, because it, like I said, the Lagrangian had an infinite number of terms. In principle, there's an infinite number of Feynman rules. But there's a definite set of rules for how big any particular contribution is going to be. And so you can clearly identify which contributions you need to calculate at any particular level in the coupling in the fine structure concept. So, and I can say that these, so the photon in this picture, this is called Coulomb gauge, which is a more physical way of describing the photon, where there's a, this photon, this version of the photon is exactly what mediates the Coulomb force, the 1 over r squared, the Q1, Q2 over r squared, the force, the Coulomb's force law. It's exactly what mediates that, and it's easy to identify as such. This is a transverse photon, and so this mediates magnetism, basically. There's a spin-dependent sigmas, a spin matrix, there's spin-dependent contributions, and so on. There's a relativistic kinetic energy correction that I talked about before. And this term, which takes into account all of those high energy aspects of QED that are not present in, well, the way that the high energies are present in NRQED is through this kind of a contact term. And what I mean by that, well, basically what I'm going to be needing to do is to actually calculate the value of that contact term. So I'm going to talk about it in more detail now. So I'm talking about the calculation of a term like this. Where does this come from? This is the NRQED picture of the contact term. In QED, we might consider a graph like this, where the electron up here and the muon down there exchange maybe 3 photons. So we might consider a graph like that. The typical energies and momenta that are going through a diagram like this are of order of the electron rest mass, or more. So the constant wavelength of the electron, that is the typical size of the diagram, like this physical size in meters, is small compared to the Bohr radius, to the size of an atom like muonium. So you might draw the picture like this, that this high energy quantum electrodynamic thing is physically small compared to the size of the wave functions. We can make this quantitative by looking at the constant radius of the electron and the Bohr radius. And so we are going to model this kind of a process just by a point-like interaction in our NRQED. So that's how NRQED takes into account the relativistic effects that are actually present in nature and they're present in QED. And the way they're taken into account in NRQED is through the value of these contact terms. And by knowing the value of that contact term and taking it basically an expectation value in the states of the system, we can calculate the corrections to the energy levels. So this is the plan. Find the values of the contact terms, these coefficients, and then we'll know what effect those have on energy levels. That's the part of the calculation I'm doing now. This is it. I need to calculate the value of those contact terms. So if I was calculating in order alpha to the 6, this capital C is well, it's an imaginary number in our case. It tells the if the positive particle had a charge Z times the electron charge, then this is we would be looking at power of Z to the 6. For our case, capital Z is 1. There are other systems where capital Z can be 2. Like if you took helium and I took away 1 electron, so you had an helium ion, you would have 2 protons, 1 electron, and that would be a Z equals 2 system. So the Z just allows you to kind of keep track of how many basically interactions that involve the positive particles there are, but for our purpose, for muonium, Z is 1. Anyway, so these kind of diagrams would contribute in order alpha to the 6. And one would have to calculate them in QED and then find the contribution they give to that matching coefficient. And that's what has to be done at alpha to the 6 to get the results at alpha to the 6. That has been, in fact, that was an earlier project that I was involved in, just to do this out. So that being successful, I was encouraged to think about going on to the next level. These are also alpha to the 6. Now there's a virtual photon up here, and there's 2 photons being exchanged between muons and photon. And so it's another kind of contribution. At the level alpha to the 7, the contributions that have not yet been calculated, the recoil corrections to them, are ones with 4 photon exchange, 3 plus 1 virtual photon, or 2 photon exchange and 2 virtual photons. And those are my 3 projects. Yes. The 4 photon exchange, I've drawn one diagram, but really there's 4 factorial diagrams because those photons could cross in any of 4 factorial ways. Okay, so there's really more diagrams than that. I haven't actually worked trying to reduce those further yet. For these kind of diagrams, there's a number of them. I think, yeah, so there's a number of them. Anyway, there's more or less 48 distinct diagrams, of which 26 are independent, as there's like symmetries that can make some diagrams equal to others. And I'll talk about this last sentence a little bit later. For diagrams with 2 photon exchange, there are quite a few different ones that kind of have that description. 19 of them. When you get, so what do you have to do? You have to write down a diagram. You have to do a direct trace to calculate the basically the gamma matrix structure. That's the first step in doing the calculation. You can imagine about 16 or 18 4x4 matrices all multiplied together, and then you have to take the trace, which is the sum of the diagonal elements. Fortunately, we have computer programs that can do that very efficiently. So that's not hard to do. And then you have to calculate some integrals, because each of these Feynman graphs for every loop involved in the Feynman graph, this graph has 3 loops. You can, just kind of like circuit theory, you can measure the number of loops. There's a 4-dimensional integral for each loop. So these integrals are, you might say, 12-dimensional. And there's some 9,000 separate ones of them. Okay, so it's could be considered a fairly substantial calculation. Because each one of them could be pretty complicated. What's wonderful about this project is that in the last, 20, 15, 10, even 5 years, new methods have been developed to do these calculations of integrals that just were not known before that. That allow these 9,000 sub-integrals to be reduced to a much smaller number of simpler integrals that now actually have to be calculated. This is kind of a technical thing. The method for reducing the number of integrals to be done is sometimes called integration by parts identities. But what these really are is just identities among these this little d here means this is instead of a 4-dimensional integral, we're using something called dimensional regularization, which means we're integrating not in 4 dimensions, but in d dimensions, because by choosing the value of d, we can eliminate or regulate ultraviolet and infrared divergences in the integral. So we're doing d-dimensional integrals. That's what that little d is. And this looks like a integration by parts kind of thing, where we're integrating over q, we take the derivative over q, and one can show that in this dimensional regularization scheme, those which can be reduced to a surface integral, therefore, all vanish. And so therefore, we can come up with a bunch of identities that relate one integral to another. So there's a bunch of identities that relate one integral to another. And so then you can develop a systematic application of that to take perhaps complicated integrals, use these identities, and relate them down to a smaller set of simpler integrals, and which are called master integrals. Those are the ones you actually have to calculate. And so here's just an example of a 3-loop master integral that one might have to calculate. Yeah, I can see that my time is running short. So I will be kind of quick, but just to say that it has been a wonderful thing for me to see how methods that have been developed to actually calculate these integrals that were just not known even a decade ago for sure, but are so powerful. So I'm going to take an example, which is this. This is just a 2-loop integral, so not a 3-loop integral, just because it's simpler. It has one free variable, which in my problem is the ratio of the electron to the muon mass. So it's a small parameter, but I'm going to consider it to be a free parameter. So it has one parameter. I'm going to imagine what happens when you take the derivative of that integral with respect to x. Take the derivative with respect to x, and then use these integration by parts identities to reduce it down to the master integrals. One gets, and I'm going to call that integral J2. I'm going to call it J2 just to give it a name. When I take, so there's J2, that's that same integral. When I take the derivative with respect to x, I find that the derivative of J2 with respect to x can be written as a combination of 3 integrals, J1, J2, and J3. J2 is the same one as we started with. J1 and J3 are 2 others that you have to add to make a set which closes under taking derivatives. Okay, so I'm going to now supplement the one I want, J2, by 2 other guys, so that when I take the derivatives of J1 and J2 and J3, I can write those derivatives in terms of J1 J2, and J3. So I can write this whole set of differential equation as the derivative of this vector of three integrals is a matrix times that same vector. And if I can solve that differential equation, I have the value of my integral. So that's kind of cool. Solve a little first order, linear, homogeneous, differential equation, and I can do my finite integral. What makes it hard is that the coefficient matrix depends on the independent variable. Okay, so otherwise you're forcing differential equations that allow you to do the solution. Okay, but it becomes more interesting when it depends on the independent variable. A technique that was found to be useful in this case is to, instead of studying the original set of J1, J2, J3, study some linear combination of J1, J2, J3, so that the differential equation becomes simpler. And up until recently, people just had to do that by hook or by crook, you know, try different things and hope for the best. Lately, there has become systematic methods for reducing by changing basis basically of the dependent variable. Capital T is a 3x3 matrix in this case, where the new equation looks like the derivative of this I guy is a very simple function of x. Capital little a, little b are just constant matrices. And the dependence on the, what epsilon is, it measures the difference between the d parameter, the d dimensions of spacetime, and 4. So epsilon is actually going to go to 0 eventually, because d is really 4 in our spacetime. Okay. So this means that this differential equation can be solved using a perturbative method. You can say that I'm going to look at a term in the solution with no epsilons, with 1, with 2 powers of epsilon, and so on, and solve the differential equation perturbatively. And this is exactly what we need. If I plug that presumed solution into the equation, which is here, because of that simple power of epsilon there, if I look at all the terms on this side with no epsilons, there's only 1. On this side, there's no terms with no epsilon. So at lowest order in epsilon, my solution is just a constant. That's simple. At the next power of epsilon, order epsilon to the first power, I get this equation. So this is what I had before, a constant. I divide by x or 1 plus x, and then I have to integrate to get the I want. And that would give you a log of x or a log of 1 plus x. At the next step, I have to take those logs and I have to divide by x or 1 plus x, and I have to integrate again. That gives a bilogarithm. At the next step, I have to divide by x or 1 plus x and integrate again. And this is like, it's called an iterated integral. These functions have been studied. They're called harmonic polylogarithms. And they're actually well known and well studied, and there's computer programs that allow you to work with them. And so by doing this process, I am solving my integrals, my master integrals, and I'll plug back into the original formulas and therefore find the corrections to the energy levels. And so that's the plan. Okay. I'm working on each master integral. There was 139 for one part of the process. Some of them have to be evaluated to power of epsilon, up to epsilon to the 8th order, which is kind of a big process. So it's not to say it's still not a lot of work, but it's possible. And I'm confident that when finally all renormalizations are done, when everything is put together, I will be able to take the limit that epsilon goes to 0 and have an answer, which I'll be able to share with the experimentalists, and we'll see what comes about. So I think I'm going to end at that point, and I thank you so much for your attention. I'd be happy to have some questions.
Thank you very much, Greg, for this nice presentation. So please questions first from the students maybe, and then
So, I noticed on the Feynman diagrams.
Yes.
You only had, photons jumping on the top and not on the bottom. Why is that?
I would consider photons on the bottom, but, the difference kind of between the top, which is an electron, and the bottom, which is a muon, is that the electron has mass density. It's electron mass and muon mass. Otherwise, they're pretty much identical particles as far as QED is concerned. So I'll take all my results, which are a function of x, for the photons being on the top, and I'll take those same results as a function of 1 over x. And then that tells me what happens if the photons are on the bottom, because now the muon is the one getting the work. There's also other graphs with photon, one on each side, perhaps. Okay, that's another calculation. But yes, that's a good question. Thank you.
Thank you.
Yeah, no, it's very nice that by taking a function that now I'll know what the function of x is, and then looking at the function of 1 over x, I'll be able to get all those other graphs.
Yeah, so you said that during your, that you mostly use Z as kind of a way of tracking orders of corrections. But there still has to be some type of way by which the electron becomes attracted to / bound to the muon. So what is that? Is it just like
The scheme is to start off with you might call it the bound state equation or the beta Salpeter equation of nR2d, which is an equation where there's a Coulomb photon being exchanged between the two charged particles, and 2 Coulomb photons, and 3, and 4, and up to an infinite number. And somehow summing up that large set of contributions to make basically it turns into a Schrodinger equation, the Schrodinger equation. And so that's the starting point. And then this perturbation scheme is built on top of that. Very similar to just quantum mechanical bound state perturbation theory. And so now I'm talking about some of the perturbations that then correct the results of that basic theory. Yeah, so yeah, it's a very interesting aspect of the problem to see how you can sum up all those diagrams and get a Schrodinger type equation that I didn't really say anything about today. But yeah.
Yeah, I have in fact 3 questions.
Okay.
Yeah. So first, I mean, we all know that the solution of a differential equation requires at least one initial condition. So the initial condition in this case is easy to obtain because it's an easier integral.
Yes, I did not mention that, but I if I'd have had another 15 minutes, I would have.
Yeah.
Yes, it's a first order equation. You definitely need a boundary condition. The boundary condition that is appropriate here is at x equal to 0. If I go back to the original integral, here, if x were equal to 0, this integral would be substantially simpler than what it is. And in fact, it would be exactly calculable.
Yes.
And so, yes, that would be, that's where
Yeah.
we use for a boundary.
Then another something. I mean, you've shown, I think, not all diagrams, but representative diagrams. Now, it is known, for example, that in multi-loop calculations, dimensional regularization, there is a little bit, I think, a pitfall, namely if you have, let's say, a self-energy insertion, yeah, and then on both sides, you are radiative recoil, your recoil photons. Yeah. So then this inner insertion of that self-energy thing
Yeah.
has a 1/epsilon term. And then you need to evaluate, so to say, the outer integral to order epsilon, or in this case, if you have two things, even to order epsilon squared. Does that pose any problems?
Interesting, aspects, yes. And in fact, it's a little bit worse than that, because when you do this integration by parts reduction to simpler integrals, it turns out that in terms of epsilon, it's order 1/epsilon to the 4th power times these master integrals. Okay, well, that's just the price you pay.
Yeah.
And the master integrals themselves for 3 loops start off at 1/epsilon cubed.
Okay.
Those 3 loops. So you must evaluate the master integrals. You have to have the 1/epsilon cubed part, 1/epsilon squared, 1/epsilon constant, epsilon to the first, epsilon to the second, and third, 8 powers.
Yeah.
So that's why this perturbative in epsilon method makes that possible.
Yeah.
Yeah.
And now my third question, you've emphasized a number of times that you're going perturbatively in epsilon. Now, the other question would be, would it make sense to not only solve this perturbatively in epsilon, but also perturbatively in x? And then, just, stop at a given order x to the 30, yeah? And, given that x is the mass of the electron to the muon, which nevertheless is 1/200, maybe would that simplify things?
Turns out surprisingly, no. I mean, if you said x to 0, yes.
Yes.
Simplifies things.
Yeah,
But my original intention was to calculate similar corrections for positronium,
yes,
electron positron, where x is 1.
yeah,
In calculating for positronium, I ran into these kind of integrals. And again, surprisingly, by putting in x artificially into the positronium integrals, then this method it's called the method of differential equations, can be used to calculate the integrals. And so basically, you get Muonium for free,
yeah,
because it was easier to have that parameter x available to use to take a derivative of than not to have x.
yes,
At x equals 1, the integrals are really hard, and I can't actually do them. So x equal to 0, I can do them.
yeah,
If I can find the differential equation that relates x to 0 to x to 1,
yeah.
then I can get all values of x.
For muonium, of course, x is perturbatively accessible and it's
Yes.
small.
Yes, it is.
So for muonium, if you want to extrapolate to positronium, you can't do a perturbation. But
Right.
if you were to only focus on muonium, could you do a perturbation next?
Nobody has done it. So maybe that answers, probably you can,
Yeah,
but since it hasn't been done and it's been an interesting problem, like for many years, that this would be interesting
Yes.
to do. Maybe this is the best way to do it. Because I expect to actually be able to do this.
yeah,
So, yeah. Yeah,
Maybe a last quick question.
yes,
Do you have to do any kind of, do you do any kind of error control here? So if you have that many different things, you have to worry about any. I understand that ideally every calculation is exact, but with 90,000 of them.
okay, yes, I mean, always thinking about how do I know that I'm not making a mistake? Doing things, over again. I have students who, who with guidance can also do these calculations independently. So we compare. So that's another thing. Also, there are these very high powers of 1/epsilon, which had all better disappear in order for this to have been done correctly. And getting 1/epsilon to the 7th, 1/epsilon to the 6th, 1/5, all of those coefficients to vanish is a very powerful check. Then, I know what the limits are when X is 0, because that's the no recoil limit, and those have been done at this level. So I can check that my results agree with that. So anyway, always that's on my mind. And yes.
Okay, great. So since we have exceeded the time and we have also a discussion with the graduate
Okay.
students afterwards, let's thank our speaker. Have further questions, please feel free to reach him out.
People, the emphasis.